A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headaches.
If you're building anything with AI, check them out. Modal.com. Alright, we're diving into the deep end of the data pool today. Today's prompt from Daniel is about the architectural tug-of-war between specialized time series databases like InfluxDB and the conventional SQL world, specifically looking at how things like TimescaleDB have changed the math. And honestly, it's about time we settled this, because the just use Postgres crowd and the specialized or bust crowd are starting to look like rival sports fans.
It's a classic engineering dilemma, Corn. And I'm Herman Poppleberry, by the way, for anyone who hasn't had the pleasure of hearing me geek out over storage engines yet. This topic is actually incredibly timely because the sheer volume of data we're seeing in 2026 is hitting a breaking point. We aren't just talking about a few server logs anymore. We're talking about every smart toaster, every industrial sensor, and every high-frequency trading bot spitting out thousands of data points per second. By the way, quick shout out to the tech powering us today. This episode is actually being written by Google Gemini 3 Flash.
Gemini 3 Flash, huh? Hopefully it knows its way around a bee tree better than I do. But seriously, Herman, let's set the stage. Why is time series data such a headache? On the surface, it's just a table with a timestamp, a name, and a value. My spreadsheet can do that. Why do we need these massive, complex systems just to track how hot a server is getting?
It's all about the access patterns, Corn. Think about a standard relational database like your classic Postgres or MySQL. They are built for what we call CRUD operations: create, read, update, delete. You're moving accounts around, updating profile pictures, deleting old comments. It's very transactional. But time series data is a different beast entirely. First, it's almost entirely append-only. You rarely go back and update the temperature a sensor recorded 3 hours ago. If you do, it's an outlier. Second, the workload is overwhelmingly write-heavy. You might be ingesting millions of points a second, but only querying a tiny fraction of that. And third, the queries are almost always range-based. You don't ask what is the value of this one specific row. You ask what was the average CPU usage over the last 15 minutes in 5-minute buckets.
So it's like trying to use a library filing system designed for finding a specific book to instead track the precise movement of every person walking through the front door in real time.
That is actually a great way to put it. A standard B-tree index, which is what most SQL databases use, starts to scream when you throw millions of time-ordered inserts at it. The index has to be constantly rebalanced, and as it grows larger than the available RAM, your write performance falls off a cliff. That's where specialized stores like InfluxDB come in. They looked at that cliff and decided to build a different mountain.
Okay, so let's talk about that mountain. InfluxDB version 3.0 came out late in 2024, and it was a massive shift, right? They moved to a columnar engine. Walk me through why that matters, for a guy just trying to keep his dashboard from lagging.
It's a huge shift. In the old days, Influx used something called TSM time. Structured merge trees. It was great for writes, but could be a bit of a nightmare for memory usage, especially with high cardinality. Cardinality is the silent killer in time series. If you're tracking 100,000 sensors, and each sensor has 10 different tags like location, version, and model, the number of unique combinations explodes. InfluxDB 3.0 moved to an architecture built on Apache Arrow and data fusion. It's columnar now.
Columnar. So instead of storing row A, then row B, it stores all the timestamps together, then all the values together.
Well, I shouldn't say exactly, I promised I wouldn't. But yes, that's the core of it. When you store all the temperatures together in one block, they look very similar. 68.5, 68.6, 68.4. Because the data is so similar, you can compress the living daylights out of it. We're talking about 90% storage reduction in some cases using things like gorilla compression or delta encoding. If you're storing petabytes of data, that's not just a technical win, that's a massive save your job win on the cloud bill.
I like saving jobs. But here's the rub, Herman. InfluxDB used to have its own language, Flux, which was, let's be polite and call it unacquired taste. Now they're moving back to SQL. Doesn't that mean the specialized part is starting to blur? If I'm writing SQL anyway, why wouldn't I just stay in the warm, comfortable embrace of PostgreSQL?
That is the million-dollar question, and it's why TimescaleDB is so popular. Timescale is essentially a set of extensions for Postgres that turns it into a time series powerhouse. They had this concept called hypertables. To the user, it looks like one giant table. But under the hood, Timescale is automatically partitioning that data into chunks based on time. So, when you query the last hour of data, Postgres only has to look at one or two small chunks of data instead of scanning a billion-row table.
So it's like having a giant filing cabinet. But Timescale is the intern who automatically organizes everything into folders by date, so you don't have to dig through the whole thing.
Right, and they've added their own columnar compression too. In 2025, Timescale version 2.15 really upped the ante. They claimed their hypertable implementation could handle 2.5 million writes per second on a 16-core instance. That's getting very close to what the pure specialized stores can do.
2.5 million points per second? That's more data than my brain can process in a lifetime. But okay, if Timescale is that fast, and it's still Postgres, meaning I can use all my favorite tools, my ORMs, my existing backup scripts, why would anyone ever leave? Why go to InfluxDB? There has to be a catch.
The catch is usually operational complexity and purity of the workload. InfluxDB 3.0 is built to be cloud native and serverless first. It's designed to scale horizontally in a way that Postgres, even with Timescale, can struggle with. If you are a massive telco or a global IoT provider, and you need to scale to 100 nodes to handle the ingestion, doing that with a relational database involves a lot of moving parts. You're dealing with write-ahead logs, replication lag, and the overhead of the relational engine. InfluxDB is stripped down. It doesn't care about your foreign keys. It doesn't care about complex ACIC transactions across multiple tables. It's a Ferrari built for one thing, going fast in a straight line.
And Postgres is more like a very fast, very reliable, heavy-duty truck. It can carry a lot of different types of cargo, and it won't break down, but it might not win the drag race against the Ferrari.
That's a fair analogy. One of the biggest things InfluxDB does better is data lifecycle management. They have retention policies baked into the core. You can say, keep high-resolution data for 7 days, then downsample it to 1-minute averages for 30 days, then delete it. In Influx, that's a one-line configuration. In Postgres, you're writing cron jobs, managing table drops, or using Timescale-specific API for it, but it always feels a bit more bolted on.
I've seen those cron jobs fail, Herman. There's nothing quite like waking up to a distful alert because your cleanup script decided to take a vacation. But let's talk about the cardinality explosion you mentioned earlier. I've heard this is the Achilles heel of InfluxDB. If I have too many unique tags, the whole thing just falls over?
It was a huge problem in InfluxDB version 1 and 2. They used an in-memory index for tags. If you had a million unique combinations of tags, your RAM usage would just skyrocket until the OOM killer, the out-of-memory killer, came for your process. InfluxDB 3.0 claims to have solved this by moving to the columnar format, which handles high cardinality much more gracefully. But ironically, this is where SQL databases like Postgres have always been strong. Postgres doesn't care if you have a billion unique values in a column, it just indexes them on disk. It might be slower to query, but it won't crash your server just because you added a new device ID tag.
So, if I'm an engineer at a startup, and I don't know if I'm going to have 10 sensors or 10 million, Postgres feels like the safer bet. It's the nobody ever got fired for buying IBM of the database world.
For 90% of use cases? Absolutely. If your data fits on one big server, just use Postgres is almost always the right answer. but we need to look at the other 10%. Let's look at a case study. Imagine a fintech company. They're tracking every single trade on the New York Stock Exchange. That is a massive, relentless stream of points. They need to do gap filling, where if a stock doesn't trade for 10 seconds, the graph shouldn't just have a hole in it. It should show the last known price.
Oh, I hate the holes in the graphs. It makes it look like the world ended for 10 seconds.
It drives traders crazy. Now, specialized stores have built-in functions for this. Influx has window and interpolate functions that are highly optimized. Postgres historically struggled with this, although version 17 and 18 have introduced better gap filling support. But if you're doing this at scale, the specialized engine is going to be more efficient at those specific time math operations. Another big one is late arriving data. Imagine an IoT sensor in a rural area. It loses its connection, stores data locally for 3 hours, and then suddenly dumps all those 3 hours of data into your database at once.
The burst problem.
Right? A specialized TSDB is usually designed to handle those bursts and backfill the data into the correct time slots without locking up the whole table. In a row-based SQL database, inserting thousands of rows into the middle of an old index can cause a lot of disk IWAO and fragmentation.
Okay, so let's talk about the great convergence Daniel mentioned in his notes. It seems like the walls are coming down. Influx is doing SQL. Postgres is doing columnar compression. Even BigQuery and Snowflake are getting into the time series game. Is the specialist store eventually just going to become a feature of the big players?
We're seeing that happen right now. Look at Microsoft Fabric or Google BigQuery. They are increasingly positioning themselves as the one-stop shop for all data, but there's a cost to that. Those systems are expensive and they often have high latency. If you need a dashboard that updates every 500 milliseconds for a factory floor, you aren't going to query BigQuery. You need something local, something fast, and something specialized.
That brings up a good point about the ecosystem. If I'm using InfluxDB, I'm probably also using Telegraph for collection and Grafana for visualization. It's a very tight, well-oiled machine. If I use Postgres, I have to find a way to get the data in there. Do I use a custom Python script? Do I use an ORM? The plumbing for specialized stores is often much easier to set up.
That's the time to first insight metric. You can set up an InfluxDB and Telegraph stack in 20 minutes and have a dashboard running. With Postgres, you're designing schemas, thinking about data types, setting up your migrations. It's more work up front. But, and this is a big but, what happens when your boss says, hey, I want to see the sensor data, but only for customers who are in our Golds tier and haven't paid their bill this month?
Ah, the relational wall.
In InfluxDB, your customer tier isn't in the database. You have to either export the data to something else or do a very awkward join in your application code. In TimescaleDB, it's just a standard SQL join. You join your T-Sensors table with your T-Customers table and you're done. That flexibility is why so many people stick with SQL. Data never stays just a time series. Eventually, someone wants to know the who and the why behind the when.
I've lived that nightmare, Herman. Just one more column, they say. And suddenly, your beautiful, optimized time series store is being asked to act like a CRM. It's like asking an Olympic sprinter to carry a sofa while they run.
And that's why we're seeing the rise of hybrid architectures. A lot of sophisticated teams in 26 are using what I call the hot-cold approach. They use something like InfluxDB or QuestDB for the hot data, the last 30 days of high-frequency metrics. It powers the real-time alerts and the live dashboards. Then, they use an ETL process to summarize that data and move it into a Postgres or a Snowflake instance for long-term cold storage and complex business reporting.
So you get the speed of the Ferrari for the race, but you keep the heavy-duty truck in the garage for the actual work.
Precisely. And we should mention the newcomers. QuestDB and ClickHouse have been making a lot of noise. ClickHouse, in particular, has become a bit of a darling in the real-time analytics space. It's not a pure time series database, but its columnar performance is so insane that people are using it for time series anyway. It uses SIMD, single instruction, multiple data, which basically means it uses the parallel processing power of modern CPUs to crunch through numbers at a rate that makes traditional databases look like they're standing still.
I love the name ClickHouse. It sounds like a place where everyone is just really productive. But okay, let's get practical. If Daniel or any of our listeners is starting a project today, What's the decision framework? Because it depends is a boring answer, Herman. Give me some hard lines in the sand.
All right, let's draw some lines. Line number 1, cardinality. If you are tracking 1,000,000 unique entities, let's say you're a ride-sharing app, and you're tracking every individual car's GPS coordinates every second. You are going to hit the limits of a single node Postgres instance very quickly. You need the horizontal scaling and the columnar compression of a specialized store like InfluxDB 3.0 or ClickHouse.
Line number 2, the who cares factor.
Right. If the data is ephemeral, meaning you're going to delete it after 30 days anyway, don't bother with the overhead of a relational database. Use a TSDB. The built-in retention policies will save you so much operational grief. It's set it and forget it.
And line number 3, the sequel or bust factor.
If your team is 3 people and you all know SQL, but none of you have ever heard of line protocol or tag sets, just use TimescaleDB. The cognitive load of learning a new database system, a new backup strategy, and a new monitoring tool is often more expensive than the extra hardware you'll need to make Postgres go fast.
I think that's a really important point. We often talk about performance in terms of milliseconds per query, but we should talk about performance in terms of developer hours spent fixing the database at 3 in the morning.
That is the most important metric there is. And honestly, Postgres is the king of that metric. It's so well understood. If something goes wrong, you can find 1,000 Stack Overflow posts about it. If your specialized TSDB has a weird edge case bug in its storage engine, you're basically on your own, reading source code on GitHub.
Which sounds like your idea of a fun Friday night, Herman, but for most people, it's a nightmare. What about the data lake trend Daniel mentioned? This idea of putting everything in Apache Iceberg on S3 and just querying it there. Does that kill the database entirely?
It doesn't kill it, but it changes its role. In 26, the database is becoming more of a caching layer. You keep the most important, most recent data in something fast like Influx or Timescale. But for the I want to see the trends over the last 5 years query, you hit the data lake. Tools like Trino or even InfluxDB's own new engine can query those Iceberg files directly on S3. It's much cheaper than keeping 5 years of data on expensive NVMe drives.
It's like having a small fridge in your kitchen for the stuff you eat every day, and a giant deep freeze in the basement for the half a cow you bought 6 months ago. You don't want to go to the basement every time you want a snack, but you're glad it's there when you need to host a barbecue.
I am loving these food analogies today, Korn. But you're right, the storage is being decoupled from the compute. That's the big architectural shift of the mid-20s.
So, we've talked about Influx, we've talked about Postgres, we've talked about the data lake. What about the AI integrated querying part? Daniel mentioned that SQL Server and Postgres are getting better at things like interpolation. Is the AI actually writing the queries, or is it helping the database guess what the missing data should be?
It's a bit of both. On one hand, we have vector support being added to everything. We've talked about this before, the vector revolution. Now, you can actually store embeddings of your time series patterns. So instead of searching for temperature over 90, you can search for show me all the times the sensor behaved like it was about to break. The database can compare the shape of the current line to historical patterns using AI.
That is wild. So it's not just, is the number high? It's, does this graph look like trouble?
And that is where the specialized engines might actually have a new advantage. If they can bake those AI models directly into the storage layer, they can identify anomalies in real time as the data is being ingested, rather than waiting for you to run a query. Imagine a database that sends you a notification not because a value hit a threshold, but because the vibe of the data changed.
The vibe. Check for industrial sensors. We truly are living in the future. But Herman, we've got to be careful here. Isn't there a risk of over-engineering? I feel like a lot of people see these cool features and think, I need that, when really they just need a simple dashboard.
Oh, the shiny object syndrome is very real in database engineering. I've seen teams spend 6 months migrating to a complex distributed TSDB when their entire dataset was only 50 gigabytes. You can fit 50 gigabytes in the RAM of a modern cell phone, Korn. You don't need a distributed cluster for that.
50 gigabytes? I have more than that in unorganized photos on my cloud drive. That's a great reality check. If your database fits on your laptop, you probably don't need to be worrying about horizontal scalability.
Right. Start with the simplest thing that could possibly work. For most people, that's Postgres. If Postgres starts to smoke and the fans on your server sound like a jet engine, then you look at TimescaleDB. If TimescaleDB is still struggling, or if your cloud bill is starting to look like a phone number, then you start looking at InfluxDB or ClickHouse.
That feels like a very solid conservative approach, which, given our worldview, shouldn't be a surprise. Don't build a monument to complexity if a simple brick house will do.
And remember that the cost of a database isn't just the license or the server, it's the people cost. If you choose a niche database, you have to find people who know how to run it. In 26, finding a good Postgres DBA is hard enough. Finding a specialist for a brand new TSDB storage engine? Good luck. You're going to be paying a premium for that expertise.
Or you're going to be the one doing it yourself at 2 in the morning.
Which brings us back to the developer hours metric. It always comes back to that.
So let's wrap this up with some practical takeaways for the folks listening. If you're sitting there looking at a mountain of IoT data, what are the 3 things you should do tomorrow?
Step 1, analyze your cardinality. Use a script to see how many unique tag sets you actually have. If it's under 100,000, stay with SQL. If it's in the millions, start looking at specialized columnar stores. Step 2, look at your query patterns. Are you doing simple last hour graphs, or are you joining this data with your users and subscriptions tables? If it's the latter, the relational wall is going to hit you hard if you leave Postgres. And step 3, check your retention needs. If you need to keep data forever for regulatory reasons, a data lake approach with something like Iceberg is the future. Don't try to store 10 years of raw sensor data in a live database. It's a waste of money.
I love it. Clear, actionable, and it doesn't require a degree in database theory to understand. Before we get out of here, I want to touch on one more thing Daniel mentioned. This idea of boring is awesome. I think that's a great mantra for 2026. With all the AI hype and the database of the week on Hacker News, there's a real power in choosing the tool that just works.
It's the Lindy effect. The longer something has been around, the longer it's likely to stay around. Postgres has been around for decades. It's seen every trend come and go, and it just keeps getting better. It's the ultimate boring tool. But InfluxDB is trying to become the boring choice for time series by adopting SQL and standardizing on things like Apache Arrow. They realized that being different was actually a hurdle to adoption.
They had to grow up and get a job in the SQL world.
We all have to grow up eventually, corn, even databases.
Well, I'm still a sloth, so I'm holding out as long as I can. This has been a great deep dive, Herman. I actually feel like I understand why my dashboard is slow now. It's probably just too many tags.
It's always the tags, corn. It's always the tags.
Well, we should probably head out before I start asking about B-tree fragmentation. Thanks as always to our producer, Hilbert Flemingtop, for keeping us on track. And a big thanks to Modal for providing the GPU credits that power this show. They make the heavy lifting look easy.
If you're enjoying the show, we'd love it if you could leave a review on whatever podcast app you're using right now. It really helps other people find these weird deep dives we do. This has been My Weird Prompts.
Find us at myweirdprompts.com for all the links and the RSS feed. We'll see you next time.
Bye, everyone.
Stay boring. It's awesome. This episode was produced using Google Gemini 3 Flash, text-to-speech by Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My Weird Prompts, that's the close from sloth, from man, from long-eared host. My Weird Prompts, until next time, stay curious, keep weirding.